3, 2, 1. Cuidado, 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 cuidado. ¡Ah! Bien. Muy bien.
Hello, this is my calculus project for the spring 2026. My project consists of using calculus to find out the equation of velocity based on the Newton's motion law, which is force is equal to mass times acceleration. The letters are specified here. So P is air density, M is mass, A is cross-sectional area, and drag coefficient for CD, and G is acceleration of gravity. I'm gonna use laws, motion law, which is the net force is equal to the mass and the acceleration times the acceleration. I'm gonna use a couple other formulas like this one, which is terminal velocity, to define when the drag force and the gravity are equal to each other, so they kind of even out the calculations. Also, the reason I'm using terminal velocity is to kind of reduce the terms that I'm gonna use in this f of drag. Okay, so I'm gonna solve I'm gonna use the terminal velocity concept to kind of get everything in terms of mass, gravity, and velocity. So terminal velocity is when the mg is equal to minus 1/2 pa. I'm gonna focus on the negative sign of the drag force because it's the sign that applies whenever the rock is going up. When the rock is going up, the drag force acts as a negative force, trying to prevent the rocket from going up, right? Because when the rocket is going up, the drag is basically acting in this direction. So that's why it's negative. Negative P times the cross-sectional area times the CD times B square. This B square is going to become BT because we're solving for terminal velocity, right? So this thing is just going to become basically, well, if we want to have everything positive, it's going to be just BT square equals 1/2 PA CD VT square, right? This T is a subscript, so it's just to determine VT. Now, well, actually I'm gonna keep the negatives on here, right? Now I'm gonna substitute everything into this equation, right? So now I have M times A acceleration, which I'm gonna use dv over dt because acceleration is just the derivative of velocity over time, with respect to time. And then we have negative mg minus, and we're gonna use this term, so it's gonna be minus mg over vt. Now I have everything right on this. Well, everything just I'm just missing the b square, right? So times b square. Why? Because I substituted this whole term by this, right? To kind of make this simpler. Now I'm just gonna play around with this expression. So I'm gonna divide both sides by mg. So I have 1g here. So if I multiply both sides by the reciprocal, obviously, right? This is I'm just gonna go fast because I don't want this video to be really long. So now I'm gonna have 1g times dv over dt equals -1 minus mg. That's gonna cancel, so I'm gonna have vt square. Oh, this is supposed to be square. Sorry. Now that I have that, I'm gonna try to integrate both sides. First of all, I'm gonna do partial derivatives. So I'm gonna get the dt to the other side. So this is dv equals -1 minus b square over vt square times g times dt. Right. Now I'm gonna let the negative here, and I'm just gonna take dv over 1 minus v over vt everything square equals -g times dt. Right here, now I'm gonna integrate both sides. So I'm gonna apply an integral, take the integral of both sides. Now I'm gonna multiply both, like the bottom and the top, by vt square. Right. So I'm gonna multiply everything. I'm gonna have bt square on the top, integral dv, that's for the top, and then v square minus bt square minus v square. Right. Now this is one of the parts that I most struggle with. Well, here the dt is just gonna become t final minus t initial, right? Or t0, however you want to call it, or just time minus t0. Let's go with that. 0. Now here is one of the steps that I most struggle with when doing this project, because I know this is going to be arctan. Well, at least I did know it was going to be arctan, but I didn't know what happens when you have this term, when this term is not equal to 1, because normally we see 1 minus whatever here, but not in this case, right? So it's kind of weird. But what happens is when you have an integral of 1 over a squared plus minus x squared, this is going to be equal to arc 1 over a times arc x over a plus c, obviously. So this one was one of the things that I most struggle with at the time that I was gonna take this integral, and it was kind of fun to kind of get into it and figure out why it was like that, and it was like kind of really good for me to kind of practice this. Oh, if I factor out the negative, this must be positive. Sorry. Yeah. If I factor out a negative from there, it must be positive. Yeah. Sorry, I forgot. So now I have this form, so I'm gonna just apply that to this thing. So I'm gonna have vt squared times 1 over a, which is our vt. Yeah, vt times arctan times arctan of x, well, v in this case, sorry, I got traumatized by x, v over vt. And then I'm not gonna use plus c because I have the, oh well, actually, well, yeah, plus c here, but that counts for everything in here, right? So now what I have to figure out is what is or C. To do this simplifies to VT, right? VT arc. Because of that multiplication, VT. I don't want this video to be so long, and this is equal to negative G times T minus T0. How do I find C? Well, C, we're gonna find it by the burnout velocity, which is the velocity of the rocket whenever the air or the last thrust of the rocket has gone through. So whenever all the water and all the air has exited the rocket, it's the velocity we're gonna use. So we're gonna have when V0, so burnout velocity, T is also 0 because it's the beginning, right? So then this thing is gonna become 0, and then it's gonna make this whole thing 0, and then we're gonna have C equal to this thing but with at 0 over here. That's gonna be our C. Okay, so now that I have that C is equal to VT arc tan. Well, actually I'm gonna use the other notation because I'm tired of writing arc tan all the time. Is when V0 and VT, right? So I'm gonna substitute this into here, and I'm gonna make this V plus VT tan -1 of VO, well, V0 burnout velocity over VT, right? And we're close to get the velocity function now. Why? Because now I just have to take the tangent. Well, actually divide both sides by VT first. So I can cancel that one out. Okay, VT. And then this thing will be VT over VT. And then this will cancel because if I divide by VT, this thing will cancel. Right? So now I have tan inverse. So now what I want to do is solve for this velocity. Right? So I'm gonna take the arc now, the tangent of both sides, so I can undo this tangent, right? And then I'm gonna have V over VT equal to tangent of negative G over VT times T minus T0 plus tangent inverse or arctan of BO over VT. And then I'm just gonna solve for velocity, so it's gonna be V equals VT times all that, so tan over negative G VT. Let me see if I can go to, I graphed this on Desmos, and what I got is that assuming that the burnout velocity is 30 meters per second and the terminal velocity is 16 meters per second, what we got is this graph where, like, after all the water has exited the rocket, it starts to decrease in velocity, obviously. But as you can see, this curve tells that the drag force is preventing the velocity to fall drastically. As you can see, it makes a curve. Instead of doing a straight line like this, it makes a curve, and that's because of the drag force that prevents the velocity from decreasing at the same rate. And with this graph, we can also tell that when the rocket reaches its maximum height is at 1.8 roughly, so after 2 seconds. Experimentally, we could see that in our video at the beginning of this, where the apogee is roughly 2 seconds or 1 point something, which tells us that this calculation is near where the values we should get.